Hi everyone. Today we're going to be talking about multiple regression, and we're going to talk about the regression equation, building regression model from data types and categorical predictors, the categories with multiple levels. So these are variables that have multiple categories, and we need to do some modification, building multiple regression models, and issues with multiple regression. And so let's get to it. The regression equation. So we have already gone over the regression equation in previous videos, and I wanted to bring it up again for the context of this lecture. So let's note also that we have two components here. We have a component that is more algebraic, which is this component here on the left side, and then we also have a geometric component, and we can try to visualize and understand regression from these two views, both on the equation side and the geometric side. The thing is, when we have multiple regression, it has multiple predictor variables. It's not easy to, or possible even to visualize it in a two-dimensional space. So this is why we focus more on the equation side, but the basic concepts still work, and hopefully by understanding the concept of the two-dimensional graph, just understanding two dimensions, we can understand the multiple dimension as well. So let's remember on the y, on the left side of the equal sign, this is what we call the dependent variable, the variable of interest, also called the outcome variable. So whatever thing we're trying to, usually the thing we're trying to predict is going to be on the left side here. The alpha is the intercept, so this is the y-intercept. So if everything else is zero, as you remember from basic algebra, if you have this here 0 and this value is 0, everything else is 0, then the y is going to be whatever the value of alpha is. So that's why we call the y-intercept. And the other component here, we have two. We have the beta, so this is the coefficient, and we have the x. The beta coefficient is how much the x is impacting y. And we'll see more details about that later. And then we also have an error term, and that's important because what we're doing with the regression is creating this line, which is a generalization of the point. So let's assume we have two variables, and here we have advertising, amount spent on advertising, and then on the x-axis. And then we also have revenue for the company. So this is how much a company is spending in advertising, how much the revenue that they're getting. So these are different locations, okay, different locations of each chain. So each dot is a location. So we have location here, we have this location here. This location is, let's say, in Wayne County, Michigan, and this location spends about $3,000 on advertising, but the revenue is pretty low. But if you add all the locations, you can see that we see a general trend. But notice how this line here, which is what the regression does, creates a line. It's a generalization of the points. The data itself, the points, the real chain stores and the real revenues, they're all scattered and they look in this weird cloudy shape, but the line is just one line. So the line cannot possibly be a reflection of all the complexity of the data. It's a generalization, and it's important for us to just get a sense of the trend. So in this two-dimensional space, we have what we call the predictor variable or the independent variable, and usually we put it in the x-axis. So this will be this one here. In this case, will be advertising, and the idea we build it in this way is so that we can see if advertising, or how much of the impact or the association, more precisely, of advertising is with, in this case, revenue, which is here on the left side. So, and then what is the beta? Well, the beta is the slope of the line. It's the slope of the line here. So it's the general trend of how a unit increase in x, how much it increases in Y. So actually we can kind of almost estimate it here with the graph. So you can see this is 1 unit increase in X. And so, well, let's go from here. Actually, how about we use what I just created here. So from here, let's do it. Actually, erase this one, get the pen again. So from here, we got about to 2, and then here we go to 2 to 4. So it almost looks like 2 units increase in advertising increases revenue by 10. You see this? Here 2 to 3, 3 to 4, there's 2 units. So from here to here. So 2 units increase in advertising leads it by 10. So that means 1 unit increase in advertising increases the revenue by 5,000. Because assuming this is 30. So this is from here to here is 10. So 2 units increases it by 10. So 1 unit increases it by 5. So 1 unit increase in advertising increases Y by 5. So the beta is this 5 here. So that's what beta does. It gives you the impact of 1 unit increase in the X on the Y. So we'll continue talking about this. So a regression model is an equation that measures the association between 2 or more variables. It is used to help us understand the impact of one variable on another. And we're beginning with a simple linear regression of only 2 variables. One, the predictor, here the X, and one, the outcome variable, the dependent. So now what we can do is actually we can add multiple predictors. And this is why you saw 1, you saw run before here. And this 1 means that, well, we have 1 predictor, 1 variable, but actually we can have multiple. We have a second one and we have a third one. And because maybe it's not just advertising that is going to impact the revenue. Maybe, yes, the more you spend on advertising is going to be associated with more revenue. But there are other things also that impact revenue. The quality of the employees, how many employees, or the customers, the type of customers, the location of the customers, and so on. So there are multiple variables that impact revenue in this case. And of course, in life as well, there are multiple variables that impact all kinds of things we might be interested in. So the multiple regression is just when it's a linear regression when we have multiple predictors or multiple independent variables. So let's note that when we're building a regression model, we're building a regression model from existing data. So in the case here, when we're talking about loans, these are and the interest rates of loans. This is a decision that banks make for people. The bank will decide the interest rate of somebody's loan. But even though they decide that, we may also look at the data of existing interest rates in loans and other information about the borrowers and see what the trend is or how they are kind of making this interest rate calculation. So the point is that we're building the regression model from existing data. It's always this way. So we have a data set here with an interest rate. We have verified income, debt income, credit utilization, bankruptcy, and the terms of the loan. So there are many variables, and let's note what's the unit of analysis here. Well, the unit of analysis is probably a loan. It could be a borrower, but it's also a loan. So all of these aspects, all of these attributes, which I call variables, all of these variables or attributes are attributes of a loan. So we need to make sure we understand that. And note how they're all different data types, and we'll have a separate talk about these data types too, because that's important. And also it's important to recognize the different characteristics or the values of each variable. So here we have a detailed explanation of all of these variables are, and it's really important to have them so you understand what kind of data you are working with. Unfortunately, however, often data sets do not have detailed explanation about what each attribute, what each variable means exactly in detail, and that's why you need to generate your own data set and to do your own analysis. Also note that in this data set, we have everything here that may be helpful to predict the interest rate or may be helpful to predict bankruptcy. So, for example, all of these characteristics, let's say, well, let's think of bankruptcy as the dependent variable. So let's suppose we're trying to predict, or we're trying to build a model of how different variables lead to bankruptcy or can explain the bankruptcy. So we can think, for example, well, debt to income, which is the percentage of total debt to the borrower divided by their total income, the debt to income ratio maybe can help explain bankruptcy. The higher the debt to income ratio, the more likely they are to have a bankruptcy. Maybe the credit utilization, this can help explain bankruptcy. Maybe the interest rate of the loan can be an explanation of bankruptcy. So if the person has higher interest rate, maybe it's going to be, they're going to more likely to lead to bankruptcy. The length of the loan in months, so maybe they have longer term loans, maybe that can more likely to be associated with more bankruptcy. So there we have all of these potential predictor variables that can help us understand bankruptcy. But note that often we don't have the data set all clean and all the important variables all in one single data set. So there are many other variables or many other information that can help us predict bankruptcy, where the people are from, or some other social conditions like what's going on with the Federal Reserve interest rates, or some political issues or war and so on. So we need to remember that. So building a regression model from data, OLS. So OLS is an algorithm that we're going to use. It's kind of like a framework or an approach that builds the model from the data. So we have the data first, and then we use this OLS, which refers to ordinary least squares regression, and that's an algorithm or set of instructions to estimate the slope of the line that minimizes the distance between the 2 points on a two-dimensional graph and the line. We talked about this on the previous videos. So essentially, we're getting this line here that is the best fitting line to minimize the distance of each point and the line in cumulative. So, we see all these points here, the black points, and you can create a line. Well, maybe it could be like this. Why is it not like this? Well, because the line that I just drew, it doesn't is too distant from a lot of the points. And this line here, that was already here, it minimizes the distance of all the points and the line itself. So OLS finds that perfect sweet spot, and it creates the built model. This is called we're building the model. So this is the built model. So this was the abstract one. We have this just the idea of the framework, and we need to have an approach like OLS to actually build the model and actually get those intercept values and get those beta values. And note that these here remain kind of just in the variable state. So interest rate, we don't put a specific number here, and we don't put a specific number also on bankruptcy. Now in this model here, what we're having is we're seeing how bankruptcy can be a predictor of interest rate. So the more bankruptcy, maybe the more interest rate. And that's what it looks like here, because this is positive. So it's a positive relationship. So let's look at it a different way. So after we build the model, we run the algorithm, we build the regression model. And let's assume that bankruptcy is a numeric variable. So there's multiple people can have one bankruptcy, or two, or three, or four, or five, or six. And then the interest rate is in percent of the interest rate. So I borrowed the other graph here and just plotted in here just for visualization. This is fictitious. This is made up just for us to understand the concept. So the idea here is that 1 unit increase of bankruptcy, so when a person has, well, let's do it. If a person has 0 bankruptcy, you can just actually calculate the equation. If a person has 0 bankruptcy, 0.74 times 0, this is multiplication sign, so times 0, any number times 0 is 0. So if a person has 0 bankruptcy, the interest rate is going to be 12.33. Now here, it's not really a real graph, so it would be like 0 is here. So if a person has 0 bankruptcy, then the y-intercept would be here, which is equal to 12.33, the interest rate. Now, what about if a person has 1 bankruptcy? Well, 1 bankruptcy, then it's 12.33 plus 0.74 times 1. So it's just 12.33 plus 0.74. What if the person has 2 bankruptcies? Well, then the person has 2 bankruptcies, then this will be 2, and then will be 12 plus 33, 12.33 plus 0.74 times 2, so about 1.5. So the interest rate will be as such. So these here, the model is, the built model is open enough for us to be able to predict different interest rates at different levels of bankruptcy. And that's kind of the beauty of it. And that's why it can be used in multiple different contexts. So an explanation here of how to interpret this is that every additional unit of bankruptcy, the X variable here, increases the interest rate by 0.74 percentage points. So that's how we interpret this number here. The alpha or y-intercept just kind of stays there. If you want to get the specific calculation, you need to add it. But if you just want to understand the impact of bankruptcy on interest rate, in general, on average, it's 0.74. Now, the interest rate is in percent, and the amount of bankruptcy is just in count, 1, 2, or 3, or 4. So note that I wrote 0.74 percentage points. And this is important because when you're dealing with percent, you have to differentiate percentage points versus percent. If you say something increases by 0.74%, it's a little bit ambiguous because 0.74% might be 0.74% of the existing interest rate. So that's different. So in this case, it's just 0.74 points. So we got, if a person has 0 bankruptcy, it's 12.33 plus 0, as we just saw before. But if the person has 1 bankruptcy, then we add 0.74. So it's the interest rate would be 12.33.74, which is equal to about 13.7, right? Okay, so that's how it works. And we'll keep talking more about this to get this down. Now I have actually another example here. So this is a building regression model from real example data set, relatively real. So I got a loan default data set with a bunch of attributes that might be useful to predict loan default. But I'm using here some of the attributes to do a simple regression to understand the impact of income on property value. So this data set has a bunch of people in it, and each person has an income, and also they have property value. So my idea here is to understand how income impacts property value. And of course, the logic behind this, I want to see if the people with higher income have higher property value. So first we begin with the data. We use the data, we load on the OLS algorithm, and the function in R is LM. And then there's a particular syntax. So this is the syntax here. Property value is an attribute of the data set. Income is an attribute of the data set. Loan underscore sub is the name of the data set. We also call this data frame DF. And that's it. And then the OLS builds the model from the data and then creates this kind of open equation that we can use to predict different property values at different income level. And one of the most important results is this here, 23.5. And I'll show you where I got this 23.5. it's a result from the regression. It's going to be on the estimate. So when you summarize the regression, you see all the results. You see the estimate here related to the income. So that means that, and it's also significant. We got the p-value here. It's very, very low, so it's definitely significant. And then we have also R squared, which help us understand the goodness of the model, which I'll explain later. So, and also we have the intercept. Intercept is over here as well. So that's important as well. So we built this equation. We can build this equation here, assuming we have just one variable, predictor variable, and also we're forgetting a little bit about the error here, so we can forget about that for now. So we have the data set. We built the model from the data set, the linear model from the data set. We got some results. The results create or can create an equation like this. And essentially the model itself, this LM model that we built, is this equation plus the details about error. And so we can calculate property values, once again, on average, in general, from every specific income. And we can also visualize it here, so we can visualize the data. We can see a positive relationship, and we can see, if this number here is positive, then that means it's positive. That means every additional income we adding property value, the property value goes up because this is positive. If this was negative, then every additional income would keep minus, would subtracting property value. This graph, the scatter plot, is a little bit artificial because I cut up the data to visualize things and better, because real data is often much more complicated than fictitious data. But anyway, just to understand the point here, so suppose the income is 0, as we did before. So the equation, you just solve for the equation. So if the income is 0, the property value is about 337,817. And actually, we don't have income 0 here because I cut it off. But you can see the line here, the income is 0. Actually, it doesn't really work. But let's see if the, income is 1. Actually, we're not really working with 1. We're working at the tens of thousands. So, but suppose the income is 1, then the value of the property would be, you solve for the equation, 33,817 plus 23.5 times 1, and so on. And what if income is 25,000? What is the predicted property value from this model? And now you can kind of maybe visualize it a little bit here on the plot, but I want you to solve it. So pause the video right now, and I want you to tell me the property value estimation if a person has 25,000 in income. Pause the video and solve. So it's very simple. You just put the 25,000 here in the income area. You multiply it by 23,000, and then you add it, and then you get 925,000. And actually, it's kind of actually right somewhere here. So there's 25,000 somewhere over here, which it looks like close to 1 million. So it's sort of at that area, it seems reasonable here. So that's it for interpreting the regression model, and we'll continue next time on data types of variables in regression.